Hello, in this tutorial I will be providing a beginner's introduction to running economic simulations in the Julia programming language. The prerequisites for this video are some familiarity with Julia. You should probably have installed the programming language as well as the iJulia extension that lets you view Jupyter notebooks like this one, and you can find the link to this notebook in the video description. And as always in economics, it's always helpful to have a background in multivariable calculus. However, I have written this tutorial without requiring any of the techniques of multivariable calculus. And actually, I think that learning some of the economic applications of calculus before taking that class, or perhaps during, can give you a strong feel for how multivariable calculus works if that's something you're considering in the future. The situation we're going to look at today is called a tâtonnement process, and this is a process that describes the price paths of perishable goods. That's a tongue twister. In our scenario, we're going to have a market that has N traders, and we could think of these traders as, say, dairy farmers. So each dairy farmer, they're indexed by I, is going to have a flock, right? Or rather a herd of cattle that produce a certain amount of milk in each time period. And I know that I'm going to this month or this year, what have you, produce so many gallons of milk. My goal is to sell out that entire supply of milk. Because if I don't sell out, because milk is perishable, it's going to expire and I can't sell it at even a reduced price. So there's no salvage value. The other assumption we're going to make is that the demand for each good, so the demand for one trader's milk or what have you, is determined entirely by the prices. So as soon as every trader picks their price, then the amount of demand they're going to get is also determined, and it does not, for example, change from period to period. However, traders do not know the exact shape of their demand curve, so they don't have a magic formula that tells them if I make my price this, then my demand will be this. Instead, all they're capable of doing is guessing and checking. So they can throw out a price, say, hey, I'm selling milk for this price, and see how many people demand their product. And in fact, tâtonnement is a French word that means guess and check, or trial and error. So let's get started with the programming aspect. We're going to start by importing the plots package. And there are other packages you can use that will make this code a little more streamlined, but I decided to stick with just the one import for this tutorial. And kind of at the outset, we need to generate a square matrix that determines the shape of the demand curve. Remember, this is a curve that the traders are going to observe, but they don't actually know all of these values that determine the detailed shape of the curve itself. The only thing that's necessary is that the diagonal of A be negative and the off diagonals here be positive. And now we're going to generate the quantities that each trader is producing, and these quantities are known to the traders. So the first trader wants to produce 0.089, is going to produce 0.089 units of whatever her product is, and her goal is to sell just that many. And we're going to assume that the sum of all of their production is 1. This is without loss of generality. We're just picking some sort of unit to measure this in so that these add up to 1, and that's going to make the math a little easier down the line. So each trader in our market is happy, right, if the demand equals the supply. So if she can pick a price so that she will get exactly 0.0899 units of demand, then she has done well. On the other hand, if her demand is higher than this value, then she's going to want to raise her price. Why? Well, because she sold out at the lower price, right? So if she raised her price a little, then she could sell just as many units of inventory, but she would make greater profit. So if you have excess demand, you raise your price. On the other hand, if you have too little demand, then you have to throw away your leftover product. So instead of doing that, you're going to lower your price in order to attract more buyers. This also makes sense, right? And the one additional stipulation we will have is that if your price is already at 0 or is very small, you won't let your price go negative. So we're going to keep all of our prices positive in this simulation. And any price update rule that obeys these two rules is called a tâtonnement process. So the definition of a tâtonnement process is any sort of dynamic price update scenario in which prices move in the direction of excess demand. You can kind of tattoo this on the back of your hand next time you have a microeconomics exam. So the next thing we need to create is the demand function, which says what the demand for each good will be at a certain price. So the input is a n vector of the prices, and the output will also be an n vector of demand quantities, and that is what we're going to compare to these supply quantities when we compute the tâtonnement price update. So I have picked a demand function that satisfies a number of arguably realistic properties, and in this case they are as follows. If the prices are non-negative, which is by assumption, then the demand is going to be decreasing in the price of the corresponding good and increasing in the other prices. So for example, if I raise my price, then the demand for my product is going to go down. That makes sense. And also, if my competitors raise their prices, then I can imagine that people will say, oh, well, that's too expensive. I'm going to buy from the original person instead, right? So my demand is increasing when my competitors increase their prices. This is fairly reasonable, right? Not completely unrealistic to expect that this will hold in a general sense. We will also assume that the economy is what we call Walrasian. And in our case, that means that we already determined that the sum of the supplies was 1, but also the sum of the demand also has to equal 1. So this is saying that the aggregate supply, sum of Q, has to equal the aggregate demand. This is not the same as saying that every single line of the quantity demanded equals the quantity supplied. If that were always true, then we wouldn't have anything to solve, but rather we're saying that the sum here is the same as the sum of the demand output. And you can think of this as assuming that there's some kind of large match between the number of, say, dairy farmers and the number of dairy consumers, right, who are out there in the market. So the total amount of products that people are interested in buying has to equal the total amount of products that the economy is producing. And actually, this is a pretty strict formulation of it. Walras's law allows not just a sum here, but this could actually be any linear combination of the demand, equaling the same linear combination of the supply. Finally, we will notice that this demand function is homogeneous in P. And what that means is that if I took a certain price vector and I doubled it, so I took all the prices in the economy and I just snapped my fingers and multiplied them by 2, then we're going to assume that the total quantity demanded for each good does not change. Now, this might seem counterintuitive. If everything gets expensive, won't people buy less? Well, the answer, according to this microeconomic reasoning, is no. Because if everything gets more expensive, then because every single purchase creates twice as much net profit for the producers, then all the money just kind of flows back, and it makes no difference with regard to the overall trading behavior. That has to do with the kind of exchange economy that we are theorizing under the hood here. And what this means practically for us is that we can always assume that the prices sum to 1, right? If we got some greater prices, we could just divide it by their sum, and we would end up with an equivalent price that yields exactly the same demand. So let's just test out our demand function by generating some random prices. And what we're going to do now is check out the excess demand and see if we can predict how the prices should move. So the current prices, I've made a little fake data frame here, are given here on the left. And if we looked at, say, Trader 2, Trader 2's price is 0.61, and she observed pretty small demand relative to her supply. So when we take the difference, we see that it's negative. And if her goal is to achieve a much higher level of demand, then she's going to want to lower her price. So we can see that her predicted direction of price motion is negative, which is given by the difference here. Similarly, another trader whose demand exceeded their supply is going to increase their price. An important thing to keep in mind here is that the demand for each good depends not just on my price, right, that I picked for my good, but also on how my competitors are behaving. So we're going to explore this a bit through a graph of one trader's supply curve, rather demand curve. So we're going to look just at trader 1, and I've used a let block here, so you can easily switch this to trader 2 or another trader if you want to see what their curve looks like. And you'll notice that the plot took a moment to generate. That's because in Julia, it uses what's called just-in-time compilation, and it doesn't compile the plot function until the very first time we call it. If I call this function again, the plot will actually generate much more quickly because it has now compiled all the code that goes in there. So that's just something to be aware of. As you work with Julia, you might think, geez, this is slow, but then you try the same exact code once more and suddenly it goes quickly. So we're looking at trader 1, and we're going to assume that all of the other traders have fixed their prices at 2, right? So they've all put their price at 2 units of currency per unit of goods. And this trader is going to explore prices that are on the range between 0 and 5. And here I've put the step to be just a very small number so that we can produce a nice smooth curve. And what we're going to do is observe the demand at all of these different prices on the range of 0 to 5. And remember, that's just this trader's price varying while the other trader's prices stay fixed at 2. So this similar function creates basically a blank. It's filled with just sort of whatever is in your memory at that time. It creates a blank vector, and we're going to fill in this observed demand vector with the demand corresponding to these prices. So we're going to enumerate each of the prices to plot, and at the corresponding index in the observed demand container, we're going to put the demand for product I, which is 1, at the fixed prices, except instead of using the fixed prices, we're going to change the ith index of those fixed prices to the price that I've decided to plot on this range. So here we fill up our observed demand container, we generate the plot, and then I went ahead and put a horizontal line at the quantity. So in the current situation, the curve looks like this, the demand curve looks like this, and the quantity that I'm hoping to achieve, the quantity of demand I want, is right here. It looks like about 0.1. So my goal is to achieve 0.1 units of quantity. And it looks like if I want that, according to my demand curve, I should pick a price of 3. So that's really great, and it's easy to see looking at this graph what my sort of ideal price update would be, but there are a couple of idealistic assumptions that we made in creating this graph. The first is we assumed that the trader could measure the demand at all of these values between 0 and 5. However, we did not make that assumption, right? In fact, for the trader to figure out what her demand is going to be at a price like 1 or 1.5, she would have to actually spend an entire market cycle selling goods at that price and then observing how many people demanded her quantity. So she does not have the luxury of drawing this whole picture. The second thing is that because the demand for each good depends on the prices of the other goods, even if I am able to find this exact market clearing price, right, this exact intersection, when the other traders change their prices, the location of this intersection for me is going to change. So let's say that instead of the other traders selling their goods at price 2, let's say they were all at 1 instead, and regenerate this graph. Now, before we actually do it, let's predict what will happen. Well, if all of the other goods get cheaper, then I'm probably going to lose some customers because I'm competing with them. And so if I'm losing some customers, then in order to achieve the same demand, I'm probably going to need to lower my price in order to get the same intersection, right, between price and demand. So overall, what we should see happen is this blue line should move down. This demand curve will move down, or if, like many classic economic textbooks, you're putting demand on the x-axis, then it would be moving to the left. So let's go ahead and try that out. And yep, sure enough, the demand curve moved down and our intersection of price and demand has moved to a lower value. So this is the problem we're trying to solve, right? We're trying to find the price that will let everyone be at their intersection point at the same time. And the way, when we find that price, it's going to be called the equilibrium. In part 2 of this tutorial, I'm going to teach you how to find the equilibrium of this kind of market using the tâtonnement process. I'm going to put that in a separate video because this one's getting a little bit long, but you can find a link to it in the description. Thank you.